Hi everybody, Dr. Ricardo here. We are going to review the derivation of two formulas, and the formulas are for figuring out the geometry of close-packed cubic structures of metals. Okay, so for metal atoms, we tend to think of the metal atoms of actually being close-packed and actually touching one another. So the outermost shell of one atom, okay, the electrons of the outermost shell of one atom actually come into slight contact with the outermost shell of another atom, which comes into contact with an outermost shell of another atom. So there's two more in this face-centered cubic structure. There would be one over here that I didn't draw and one over here. So I could draw a similar line across this angle, but I didn't because I wanted to keep my picture nice and simple. Okay, so this video pertains to calculating the relationship between the radius of the metal atom and the length of the cell, of a cubic cell. Okay, so that's the key. So A is the length of the cubic cell and R is the radius of the atom. So we're going to do it in two cases. First, we're going to do it in the case of a face-centered cubic metal structure, and then we're going to do it in a body-centered cubic metal structure. Okay, so if you think of this, so first of all, we know that cubic close-packed structures are the only ones we're going to be responsible for in this course. We're going to skip the simple cube or the primitive cube because metals don't usually form in that structure because it's hard for the two atoms to touch, for these two atoms to get all the way across. So most of the time when we have cubic metal structures, they're going to fall into our favorite two categories, and that is face-centered and body-centered. Okay, so those are the only two you're going to be responsible for. I won't ask you any about this relationship in a simple cube. All right, so let's get started. What you're looking at is the top face looking straight down on one cubic cell, okay, for a face-centered structure. So you know that this pattern from the top looks exactly the same as it does on the bottom, okay? Plus each of these sides, right, if this is the top, each of these sides here has a similar profile. Every one of the six faces looks like this, but for simplicity, let's pretend we're looking straight down at the unit cell. If we're looking straight down at the unit cell and we say we know it's a cubic unit cell, that makes this side length of the cell equal to A, okay? This side length equal to A, this side equal to A, this side equal to A, plus if we went straight down, going down would be equal to A. So the length, the width, and the height, you can't see the height, right? Because we're saying this is the top side. The height would also be A. So this is a perfect cube, right? So I'll just draw it really quickly for you. You know, right? We're talking about a perfect cube where each side is equal to A. The sides that we can see, we're looking at the top face, right? We can see this one, right? And we can see this one. Those are the two A's that we're talking about, right? This one is this length. This one is this length. Okay, so you can't see the last one, which would be the depth, but all three sides, length, width, and height are equal to A. So every single edge on here is equal to A, and that's always going to be the case. Okay, all right, so the first thing that we can say is, let's figure out what this length is. Let's do the geometry across this right angle, and this is something that you guys have done. So if this is A and this is A and we want to find this length, let's call that C. Okay, so the first thing we know from the Pythagorean theorem is that C squared is equal to A squared plus B squared. So in normal cases of a rectangle, this would be A, this would be B, and this would be C. The hypotenuse would be C. Okay, and we'd have A squared plus B squared is equal to C squared. But in our case, it simplifies because B is not its own unique length. It's the same as A. So in our case, we have A squared plus A squared is equal to B squared. So I substituted in for B squared another A squared. Well, what is A squared plus A squared? Well, A squared plus A squared is 2A squared. These are like terms, so you can add them up. Well, then we have c squared is equal to 2a squared. All right, last step. What's the relationship between c and a? Well, if I want to get c by itself, I take the square root of both sides. The square root of c squared is just c. I wind up having to take the square root of 2. And then what happened to the square root of a squared? That just becomes a. So the relationship that we knew between the hypotenuse of a right triangle and the two lengths, when the two lengths are equal, is c is equal to the square root of 2 times a. All right, let's make another substitution. What is this length c? Well, this is really neat. You can see it right in front of you. This length c can be broken up into how many atomic radiuses of the atom I need to cross to go from this point to this point. So check this out. Here's the first one. From here to here, that's a distance of r, right? Then from here to here, there's another r. From here to here, there's another r because r is the radius. And here's the fourth r. So how cool is that? There are 4 times the radius distance to get across this face. So what do? C is not just c anymore. C is the same thing as 4r. So I substitute my 4r in for c, and then I solve for r, which means just divide both sides by 4, and I wind up with this cool relationship. The relationship between the radius and the side length is equal to the square root of 2 divided by 4. Okay, so each radius is equal to the square root of 2 divided by 4. If you wanted to figure out what this number is, the square root of 2 is a number like, I think it's 1.41, and then let's divide it by 4. So if you wanted to get the fraction, we would just take square root of 2, right? It's 1.41 divided by 4. So this guy, the radius is 0.353, okay, or 0.35, let's just leave it at 0.353. This turns out to be 0.353. 35, let's make it 4, okay? So if I know the length of the unit cell in a face-centered cubic metal, and I ask you the radius, just take the length of the cubic cell and multiply it by the square root of 2 over 4, which works out to be that number. Okay, let's do the same thing for the body-centered cube. Okay, now for the body-centered cube, remember, what do we have? We have one lattice point or one atom at each of the faces, at each of the corners always, so we know those guys are there. I didn't draw them in because it would make it too complicated, but just think of an atom there, okay? And instead of having a second metal atom in each face, we have one straight down the middle, one exactly in the middle, okay? One exactly in the middle. Okay, so the first thing we want to do, just like we did last time, is figure out what is this length. Now be careful, this length is not only just across the triangle, but it's across the triangle and also up, so it goes diagonally across the cube. So it's going to be a longer triangle than C. Well, we already know what C is from the last one, right? The relationship between C and A is C is equal to the square root of 2 times A. So we're going to reuse that in a second. Okay, so here we go. Let's talk about this triangle now. I'm going to draw it out. This triangle goes across the base. That was our C from the first one, right? Across the base. That's square root of 2 times A. But then there's another distance A up this way. And it's that right triangle that we're doing. And here's our new hypotenuse. I'm going to call our new hypotenuse D. So for this right triangle that's inscribed in the cube, right? It's kind of a 3D standing up right triangle, not just the one across the bottom. We know that for any triangle, right triangle, D squared is equal to C squared plus A squared. So here's A. But we know C now from up above. C was square root of 2 over 2. So I'm going to substitute that in for C because C was just a regular right triangle down at the bottom. So substitute square root of 2 times 2 for C squared, for C. That means I have to put it in for C, so I have to square it. Okay? All right. So once I do that, A is just A squared. So A squared plus C squared equals D squared. Okay. Well, let's simplify this. What's the square root? What is square root of 2 squared is just 2. And then A is squared. So this to here is just algebra. Okay, next thing. Here, I have 2a squared plus another a squared. So just like above, a squared plus a squared was 2a squared. Well, here, these are like terms. They're terms in a squared. So 2a squared plus a squared gives you 3a squared. Makes sense? I'm just adding 2 plus 1 equals 3. Next step, let's solve for d. Solve for d, I need to take the square root of both sides. Take the square root of this, I get d. Take the square root of this, the square root of 3. And then here, I have to take the square root of a squared, so I get a. So I come up with that d was equal to the square root of 3 times a. Whereas for a face-centered cube, it was the square root of 2 times a. So that's interesting. You get another square root of a in there, okay? So you get 3 of them instead of 2 of them. Okay, so that puts us down here. All right, and the last step is exactly the same. Okay, if I think about it, I've got my atom. Let me see how good a job I can do. Right smack in the middle, right? But then I've got my atom down here. Sorry, that looks a little bit too big. And my atom up here, right? I have 3 going across this upward diagonal, and I would have 3 going this way. So it's not just across the face. It would be any one of these diagonals like that. Okay? So same thing. Here's an R. Sorry, it doesn't look so good. Here's another R. Here's another R, and here's another R. There are 4 radiuses that I need to cross. Let me erase my D for a second. Okay? There are 4 radiuses that I need to cross to equal D. So D, in terms of radius, is equal to 4R, just like it was the last time. D was equal to 4R, or last time we called it C. Okay? And then do the algebra, substitute in for D, put a 4R in there. I'll get this formula. I want to solve for R so I can see what is the radius if I know the length of the unit cell. Well, the 4 comes underneath and I get this relationship. So I'm going to have 2 relationships that I can use on homework and tests. Okay? So we'll go over it right now and we'll be done. Okay, first relationship. If I have a body-centered, close-packed metal, and I figure out, given the density and the structure of the atoms and what kind of atom it is, you can figure out the length of the unit cell. So you already know how to do that. I have another video on that. Once I figure out the length of the unit cell, if I want to know the radius of the atom is always going to be square root of 3 divided by 4 times that radius. Okay? If I have a face-centered cubic structure, the radius is going to be square root of 2 divided by 4 times A. So that you could see that face center is a closer packed structure, right? The radii are going to be smaller. The atoms are going to be packed closer together. So the relationship is tighter. Okay? So this one came out to 0.354. This one's going to be a slightly bigger number. So let's figure out what that number is so we know what to multiply. Now again, you can just do it every time, or you can remember this decimal number. So we need the square root of 3 and then divide it by 4. So I'm going to take square root 3, that's like 1.71 I think. Okay, 1.73, and then divide that by 4. Okay, so 0.43. Okay, so my multiplier is 0.43. Take the A times 0.43 to get the R. Okay, here it's about a third, right? Take the A, multiply it by 0.354 to get the R. Okay, so my two formulas, write them down, use them. Hopefully they work. Okay. All right, let me just back out for a second so you can see the whole page, just in case you want to take a picture of it. One more. Let me autofocus. Not so good. Let me go in a little bit. It's a little better when it's closer. Let me autofocus. That's better. Okay, there's the face centered. And there's the body centered. All right, have a great day, guys. Take care. See you on the next video.